So, hi everyone. Thanks again for joining for this first early career researchers webinar. It is my great pleasure to introduce the second speaker, Dr. Eunhye Song. Dr. Song is the Coca-Cola Foundation Early Career Professor and Assistant Professor at the Industrial Engineering and Systems Department at Georgia Tech. Dr. Song's research interests are in simulation optimization, simulation design of experiments, and uncertainty quantifications. She has won numerous awards, for example, the NSF Career Award in 2021, Harold and Ing Marcus Early Career Endowment, and many others. And also, I should mention that Dr. Song has been a very active member of the Informs community. So thank you very much, Eunhye. So today she'll talk to us about the most probable best. Eunhye, the floor is yours. Thank you so much.
Thanks, Albert, for introducing me, and thanks, Riwei, for inviting me to give this talk. This is a great opportunity to share my work on selection of the most probable best. So this is joint work with my postdoctoral researcher, Tae Kim, and co-author Kyung-Guk at KAIST Business School. So at the very high level, this is a simulation optimization talk. And actually, Sarah set up the stage very well for me because this is also related to the model risk coming from input uncertainty. So let me start with a motivating example to highlight what I mean by input uncertainty and model risk. So this is motivated by the industry project that I work with, GM, General Motors. So at GM, there is an initiative called Vehicle Content Optimization, which is very high profile. The content here means the combination of the vehicle features going into a vehicle model. So for example, if it's a Chevy Cruze, you have to decide what kind of vehicle wheels or the seat material or sound system to pack it into a car so that they can sell it at the right price point. And the importance of this problem is because in the US vehicle market, most of the people go to the dealership lot and pick the car on the lot instead of actually customizing their cars. So it is very important for GM to learn what the customers like and package the car in the way that is competitive against the competitors to seize the market share. So the way that they evaluate this is with simulation. So in the content optimization simulator, they have two parts where the consumer behavior is simulated and also the dealership behavior is simulated. So for any given content portfolio, that is the portfolio that's specifying what kind of combinations will be going into the vehicle at what price point. And then they can simulate the sales volume to estimate the market share. So it turns out that this simulator is dependent on many inputs that are unknown. But one of the most important parameter is called the theta, which is the utility parameter vector. So this vector represents how much customers value each feature of the vehicle relative to the dollar value. And that is clearly unknown. If this is known, GM will be the market leader. So this is actually estimated based on the survey result. So what they do is they use a Bayesian model. They put a prior on theta and they conduct the survey and update the prior to the posterior. So it turns out that there's a huge uncertainty in this value of the theta. So therefore, the uncertainty on the posterior distribution on theta is also high. So in this situation, then what it means to pick the best portfolio when the key parameter is actually unknown, right? So to give you a high-level idea, I'm showing you the toy example. So suppose that we're comparing 4 portfolios, A through D. And on the y-axis, I have the estimated market share from the simulator. And on the x-axis, I have 7 different theta values that I exampled from that posterior distribution. So you can see that given the theta value, you have different portfolio as the optimal solution. And as the theta value changes, the optimal solution also changes from D to A. So you can do a lot of different things here. So for example, you can take a look at the mean best by averaging the performance across all the thetas and pick the best one. Or you can also do a robust optimal approach, which is to say that what is the worst case performance for each portfolio and pick the one that has the best worst case. So however, the question that I'm going to ask today is, what if GM wants to pick the portfolio that has the largest probability of being the best? So in this very simple scenario, if we just assume that all the thetas are equally probable, so then that would be the scenario D, right? Because out of 7 cases, 7 random sample of the thetas, your portfolio D is actually the best in 5 cases. So this is where the title of this talk comes from, the most probable best, because that is the solution that maximizes the probability of being the best. So actually, this kind of decision criterion is also used in the health economics analysis literature. So what they do is they compare different treatments and using simulation. And the objective there is to find the treatment that has the largest probability of the best treatment among the options. Okay, so as I said, this is a simulation optimization problem because all of these market shares they have to be estimated based on the simulation results. So if you just look at one theta value, this is a very classical problem called ranking and selection. So basically you have discrete or categorical options, and then you're simulating the performance measures and estimators are computed, and then you compare the estimators to pick the best solution among them. So this is also known as the best RM identification in the multi-event literature. But however, because of this additional layer of the uncertainty on the parameter, the problem that we have here is a little different. So I'm going to focus on the problem formulation next. So let me first introduce a few notation first. So the let's say that I'm simulating the ith alternative or the portfolio using my simulator. So here I would correspond to the portfolio, and theta corresponds to the theta vector that you sampled from the posterior in the VCO example. So I'm going to use the notation of eta I theta to represent the conditional expectation of the simulation output, conditional on the value of theta. So that would be a particular vertex that you saw in the graph in the previous slide. So clearly, the simulation output, the functional structure of the Y is unknown. So you cannot actually just compute the expected value analytically. So what you have to do is to run simulations, and you have to take the sample average, for example, to estimate that value. So I'm going to make the problem simple by assuming my theta has a finite support with equal probabilities. And this can be extended to the case where you have unequal probabilities or continuous distribution. But for the sake of this talk, I'm going to assume that. And then for any given theta b in the support of the theta, I can define the conditional optimum, which is IB. That is the solution that maximizes the true unknown mean among all the k alternatives that I'm comparing. So k was equal to 4 in my example previously. And then I can define the preference probability, right? So preference probability is defined as the probability that each solution I is indeed the best. So with this simplifying assumption with the equal probabilities, that's just, you're just going to count how many times each solution is being the best, and then divided by the total number of support points. And again, this can be extended to a general case as well by using integral. So the most probable best, as I said, is quite intuitive. It is the solution that maximizes the preference probability. So it's I star is my notation for the MPB. And that is the solution that has highest probability of being the best, or highest preference probability. So for the theory part, I'm going to assume my MPB is unique, and also my conditional optima are also unique. So with that notation, I'm going to give you a simple illustration for the 4×8 example here. So I have 4 solutions that I'm comparing. I have 8 values of theta that are equally probable, let's say. So here, the circles and the blue circles represent the true conditional optimum under each theta, okay? So if you just look at a single theta cutting across the column, that's what I call an inner problem. So that is conditional on theta I, which one is the best, right? So that turns out to be solution 1. And so that's a very classical ranking and selection problem where you have to rank among the means and choose the best one. But here in this our problem, actually we have another problem on the outer level, which is to figure out the probability of each solution being the best, and we rank among them. So there's this outer layer problem that makes the problem a little more complicated. So in this particular case, because solution 1 is the best in 4 times out of 8, that is indeed has the highest probability of being the best, preference probability, and that's the MPB in this case. So keep in mind that all of these means are actually unknown. So even though I marked with the blue circles here, that this configuration is unknown to us, we actually have to learn these. And 2 more notations that I'm going to introduce here is the favorable set and adversarial set for each solution I. So the favorable set is defined as the set of parameters that make my solution I to be the best. So in this particular case of solution 1, that is these 4 solutions. And the adversarial set is just simply the complement of that, which is just these 4 other parameter values. So again, these have to be estimated. So the research question here is, how do we actually allocate my simulation budget to estimate this very efficiently? So let's talk about the learning problem. So what I call is this, this problem as the MPB learning problem. So to set that up, I'm going to define my learning models. So the reason that I need the model is because the means are estimated based on the simulation outputs. So I need a statistical model that can update my belief about the mean performances of each solution parameter pair. So with that, I'm going to assume a normal conjugate model, which means that my simulation output is assumed to be normally distributed with the mean eta. So eta is the conditional mean that I defined previously. And lambda square is representing the stochastic variance. So that is the run-to-run variance of my simulation output. And because I'm taking a Bayesian approach, I'm also going to use a prior model on the eta. So the prior model on eta is distributed with another normal distribution with the prior mean, the mu, and the sigma squared is representing the prior variance. So as I said, these values have to be estimated based on the simulation results. And we have k times b number of the solution parameter pairs. Again, k in the toy example is 4, b in the toy example is 8, right? So the total budget n has to be allocated to these kb number of pairs. Now, I'm going to use the notation of alpha to represent the fraction of the total budget assigned to each solution parameter pair. And I'm going to ignore the integrality condition because n is typically very large. So with that, if I assume a non-informative prior, which means that I'm going to assume the variance, the prior variance to be infinity for this eta, so then I can simply update the posterior distribution of eta to be another normal distribution with the following parameters. So if you look at the posterior mean, first of all, that is just the sample average of the replications that you ran at the I, theta b. Okay, and the variance of the mean estimator eta is also very simple. That is equal to the sample variances, sample means variance. So that's equal to the simulation variance divided by the number of replications. So with this model, what I'm going to do is, even though my eta is unknown and is treated as random, I'm going to use this posterior mean as my plug-in estimator for the mean performance. So suppose I did that. Now, again, the question is, how do we actually allocate these alphas, right? So conceptually, these definitions make sense, but we actually haven't talked about how we can choose these alpha values. And this is related to the optimal budget allocation problem Sarah was talking about before. So to that, I'm going to first have to establish a measure of efficiency. So for whatever budget that I'm given, I want to maximize my efficiency of the simulation experiment design. So to do that, I'm going to first think about how I can estimate the conditional best. So simply the sample conditional best is denoted by IBN, and that is based on the posterior means, I'm going to pick the best one. So keep in mind, if I don't have n, the true conditional best is defined using the etas, but because etas are unknown, I'm going to define it with the posterior means mu. And that's my sample conditional best. And once you figure out the sample conditional best for all of the theta b's, now you can also define the sample MPB. So we can, similarly, as the MPB is defined, we can count how many number of times each solution is being the sample conditional best. So then my measure of efficiency here is the probability of false selection. So this is a very popular measure in the simulation ranking and selection literature. So this is defined as the probability that my estimation-based, simulation-based estimator of the MPB is not equal to the true best. So if we pause for a moment and think about it, for any given simulation budget n, the most efficient algorithm, if I use this as an efficiency measure, is going to minimize the probability of false selection, right? So that event is, the false selection event is something that you want to avoid. So it turns out that doing this is extremely difficult, even with a lot of structural assumptions, because probability of false selection for any finite n is very hard to analyze. But instead, one thing you can do is to take a look at the asymptotic statement. So in other words, if my simulation budget goes to infinity, what happens to this probability of false selection? So what happens is that false selection event is becoming a rare event in the limit, because as you allocate more and more simulation effort, and if you're doing that judiciously, then clearly you are going to have to make mistakes less frequently, right? So then you look at the exponential convergence rate of the probability of false selection, which is the expression here, and take that n to infinity. And by looking at this limit, you can analyze what would have been the best allocation of your simulation effort in the limit. Okay. So this is called the large deviation rate. So in the rest of the 5 to 10 minutes, I'm going to talk about how to characterize the this exponential convergence rate of the probability of false selection. Again, sorry, I'm a little bit jumping back and forth here, but basically this problem is called the optimal computing budget allocation problem. So the objective of this is to find the alphas that are the fractions. So, if you sum them up, it has to be equal to 1, and all of the fractions have to be non-negative. So if I want to look at the objective function, as I said at the beginning, the goal is to minimize the probability of false selection, which is equivalent to maximizing the logarithmic convergence rate or exponential convergence rate of the probability of false selection. So that's the route that I'm going to take. So to talk about how to characterize this large deviation rate, I'm going to talk about going back to the toying example, and talk about how to characterize the false selection event. Okay, so clearly, if all of the conditional problems are solved correctly, right? If all of the conditional optima are found correctly, so then we're set. The outer level problem will correctly find in PB. But what I'm going to highlight in the next slide is that you don't actually have to find all of the solutions correctly for all of the problems, because not all of the conditional ranking selection problems are equally important. So to see that, let's take a look at the two cases, right? So the first case is I'm going to base my decisions on the sample averages or the posterior means. And then the black circles are the ones that I identified as the conditional best. And in this first case, you're making the correct choices except for the one here. So instead of choosing solution 1 as the best under theta 4, I chose solution 2 as the best because sample average is noisy, and that's what happened here. So in this case, solution 1 and 2 are tied at the outer level problem because they have the equal estimated preference probabilities. And because of the assumption of uniqueness, whenever there is a tie, we treat that as false selection. So in this case, the false selection event happens because we cannot tell solution 1 as the best solution. But if I make a choice of 2, right? So I was right at everywhere else except for theta 8, under which I wrongly choose solution 3 as the best. Indeed, I still have the correct selection because now solution 1 is still the dominant one on the outer level problem. And the fact that I made a mistake here is not really hurting me on the outer level ranking selection problem. So this actually gives you an intuition that the importance of these problems are different, and we have to measure that to correctly characterize that logarithmic convergence rate of the probability of false selection. Right, so with that, I'm going to just give you the high-level intuition and the results of the convergence rate. So that convergence rate is actually lower bounded by this product of the two functions, W and G, we identified. And that minimization here is taken over all of the suboptimal solution versus parameter pairs. So those are the same as the orange set that I highlighted in this figure. So those are the pairs excluding all the conditional best paired with its own parameter. So whichever is going to obtain the minimum here is going to slow us down, right? So later we're going to actually use that to design a best experiment. So first, I'm going to describe what G is. The G function is defined for each I and theta B pair. So this is actually measuring how fast the probability of the event converges to 0, where the event is the solution I is falsely beating the conditional best at the particular theta B problem. right? So as I said, if all of the inner problems are solved correctly, then we're going to have the correct solution outer level. So it matters to solve each comparison, it matters to do each comparison correctly. And this is measuring how fast that the probability of making a mistake converges. So if you look at the expression, this is actually a function of the unknown mean. So what happens is you're taking the difference between the mean of the true best under that theta b with the I solution, and then you square that and you divide it by some function of the variances. So this actually makes sense because if your mean difference is small, that's going to make this g function small, and that's going to make the minimum, draw the minimum down. So that, in other words, if the means of the two solutions are close to each other, so then that becomes a difficult problem to solve because it's more likely that you're going to make a mistake. And a similar analogy can be made about the variance as well. Keep in mind, these variances also are a function of the fractions of the simulation effort that you're giving. So these are going to be your decision variables later on when I set up the optimization problem. And the other part of this expression is the balance weight. So the balance weight is the W. So it's actually measuring how important each I theta B pair is to the false selection event at the outer level. Okay. So, so this expression for the balance weight is actually very simple. However, it is hard to explain. So what I'm going to do is to remain at the high level and give you the intuition. So for any fixed solution I, so if you just cut across the row here, right? So this weight is smaller if the theta b is included in the MPB, most probable best favorable set. Again, that is these four solutions here, right? So that actually makes sense because what it says is that if I fix the solution I, it is important to allocate more effort to the parameters that are included in the MPB's favorable set. And that's exactly what you saw here, right? So in this example, because one is more important than two, because that parameter is actually, it matters more to identify the best as the MPB under theta 4. And so that's the first fold. And the second fold of the intuition is the for the fixed theta b, cutting across the column, the weight is smaller if the solution's preference probability is higher, right? So what that means is if I have a solution, let's say solution 2, that it has higher preference probability, which is 1/4 in this case, than solution 4, which is 1/8. So then it is more important for me to identify or allocate more effort to the solution 2 because there is a higher chance that you're going to make a mistake in the comparison in the outer level. So that's the high level intuition. And the reason that the balance weights are smaller in this cases is because, again, those are more important and the minimum is going to determine the overall convergence rate. All right. So with that, I'm going to plug this expression back into my OCBA problem, right? Keep in mind here, it used to be the logarithmic convergence rate of the PFS. Now I'm replacing that with the lower bound expression that I had in the previous slide. And this turns out to be a concave problem in terms of 8 alphas, right? So this can be solved simply using the KKT conditions. And here are the set of optimality conditions that the fractions have to satisfy. So the first one is that what I call a global balance condition. So what that means is that the fractions that I'm giving to each conditional best relative to its stochastic noise, the simulation variance, has to match this balance equation. So the other side is that the summation of the same ratio for all of the suboptimal solutions under that theta. So this balances out, how much effort that you're going to give within each subproblem of theta b. The other one is the pairwise balance condition. So in this one is that saying for all of the suboptimal pairs in the orange area here, these the product of these two functions have to match. And this is actually pretty intuitive, and you can see that from here in the optimization problem. Whichever is going to fall behind is going to draw the entire objective function down. So because you want to maximize, you want to make sure that all of these weights are bound, the products are balanced. So that's your pairwise balance condition. And last but not least, but the last condition is the fractions of the sampling fractions that you're giving to the optimal solution, the MPB, paired with all the suboptimal solutions, right? So that's these are the nodes that I'm talking about. So they have to be equal to 0 in the limit. So this has to be taken with a little bit of caution. It doesn't mean that you're not simulating them at all. Indeed, actually, you have to simulate them infinitely often, but not at the rate as other solutions. So if your budget capital N is given, you want them to be simulated sublinearly in N so that in the limit, they are negligible. And the intuition is the following. So as long as you identify which one is the best among the rest, even if you make a mistake here and say solution 1 is better than solution 2, it doesn't hurt identifying the MPB in the outer level. So that's the intuition behind why the third condition is there. All right. So unfortunately, so what I talked about so far is that when you know the true mean parameters, true variance parameters, as I said, the G function here that I introduced, that it depends on both true means and the true variances. And in reality, we don't know them. So one thing we can do is to plug in the estimates of the posterior means, but also the posterior means have to be learned in the sequential fashion as you're allocating more simulation effort. So here's the sequential version of that algorithm. So what it does at the high level is basically it's checking every time you allocate a simulation effort to see which of the balance condition is broken and allocate to the pair that is lagging the farthest behind the balance conditions. So that's the high level intuition. So then theoretical question is here, then if I do this, right? So as the simulation budget goes to infinity, am I actually going to achieve the optimality conditions that I was talking about in the previous slide? And the answer to that is unfortunately no. And so this algorithm that I'm talking about, algorithm 1 in the previous slide, actually do not satisfy the requirements. So it's not consistent in the limit. And the intuition is because of the third optimality condition, really. And because that's saying that if I have those solutions and parameter pairs included in here, I have to spend very minimal effort. And if I just follow this, and the problem is these MPB and the MPB's adversarial set is also estimated based on the simulation results. And if I just simply follow this, then there's a big chance that this is misspecified. And as a result, there is a non-zero probability that in the limit, you're not going to actually converge to the true MPB. So to tackle this problem, we improved algorithm 1 to algorithm 2. So what we did there is actually fairly simple. So for those combinations of the parameter solutions in the red box, instead of plugging the posterior mean, what we did was to sample from the posterior. Okay, so that will give the algorithm a chance to correct for the mistakes that it's making along the way based on the posterior means. While in the limit, as you're simulating more and more, the posterior distribution will converge to degenerate distribution. So as a result, a posterior sample will be very similar to posterior mean. So we're still making this sublinear simulation effort to those solutions, so thereby satisfying the third optimality condition. So we could show theoretically that this actually do have strong consistency to the optimality condition. Algorithm 2 does. So that was our theoretical contribution of the work. So with that, I'm going to switch the gear to go back to the VCO example that I talked about at the very beginning. Okay, so of course, GM doesn't want to share with me any proprietary information. So what I did was to mimic what they do with the theta estimation by generating fake survey data and fitted a distribution model for the theta. So this was actually done with the Markov chain Monte Carlo. So we could generate the 50 different values of the utility parameter vector using the posterior distribution. And the portfolios that I'm comparing are these 9 ones. So the descriptions represent what how each portfolio is designed. So for example, top 40 products, we based on the prior assumption on the utility parameter, we chose the top 40 products to fill the lot with. And because there can be stockouts, we also allow the products can be repeated, right? So for example, the second one, we have 2 items of each of the top 20 products. And what you're looking at on the last column is the posterior preferences of all of these portfolios. So these are actually the brute force Monte Carlo result, right? So you can see that portfolio 4 has the highest posterior preference of 44%, while some of the other portfolios have 0 probability. So even though your true utility parameter vector is unknown, this is very unlikely to be the best one. So the I'm going to focus on the algorithmic performance on the left-hand side graph. So the what you're looking at is the logarithmic scale of the probability of the false selection. So the faster the line goes down, that means the algorithm is more efficient because it converges faster. And on the x-axis, you're looking at the sequential simulation budget that I allocated. So there are four algorithms that are compared here. So first one is the equal allocation. So it's basically, I'm just going to equally allocate my effort to the k times b combinations of the solution parameters. And the second one is the OCBA. This is called the contextual OCBA algorithm, and it's very popular in the contextual ranking and selection literature. And the objective there is similar to us, but different. So their goal is to solve the ranking and selection problem equally correctly for all of the contexts of data. But in our case, our goal is to identify the most probable best. So this is not exactly aligned. And we also tested algorithm 1 and 2. So you can see that COCBA is actually doing pretty well in this particular example. However, algorithm 2 clearly beats the other ones. So I do have a slide on the algorithmic robustness, but I'm going to skip this for the sake of time. So I would like to say a few words about the future directions. So what we did on this work is to define what MPB is and how to find that MPB most efficiently, right? And so we have some theoretical results on that. So what's really interesting to me is that what happens if the real world sample size actually goes to infinity? In other words, instead of stopping at collecting a survey data and conditional on that, we're analyzing what the MPB is. If we can go back and increase the survey sample size, right? So that's where the money is in the industry, because they really want to know how to design that experiment, right? So one thing that is nice about the MPB is that as your real world sample size increases, that MPB actually converges to the market best, right? So if you increase the survey sample size to infinity, intuitively speaking, you have to converge to the market best portfolio. So it has the strong consistency. And secondly, we also analyze the convergence rate at which how fast it is converging to the true best. So this convergence rate actually indeed depends on how you're allocating the sampling effort at not only the simulation options that I was describing today, but also how much effort that you're allocating to each data sources. So in other words, how many questions that you're going to ask about the wheels or the colors or some combinations, right? So in other words, you can actually take a look at that experiment design and make sure that MPB is converging to the true best at the fastest rate. So that's what I'm currently working on with my postdoctoral researcher, Theo. And so with that, I'm going to conclude this talk by saying thank you for organizing all this, and I'm happy to answer any questions.